-1. Okay, so up today, we're in section 14.6, which is primarily the gradient. It's like the main thing we're going to work on. But we're going to build up to the gradient by first looking at directional derivatives. So you've heard of an x partial, you've heard of a y partial. Now we have a whatever direction I want to make up partial. That's going to be our directional derivative, or something kind of like that, at least. Because there's no real particular reason we have to go in specifically an x and a y direction to get our partial derivatives. We could go in whatever fancy direction we'd like to, and that thing has a definition and a name. It's going to be the directional derivative, and it's this limit. Right, when we looked at the x partial, we only had an h on the x value. When we looked at a y partial, we only had an h on the y value. Now for our directional derivative, we'll define our direction to be a, b, which is some unit vector over there. And we'll just add an h times a and an h times b to the x and y values respectively. And we get our definition. Here's a quick worked out example of the formal limit definition, or the formal limit example of that derivative. We won't actually be doing any of that because we're trying to stay away from some of the more tedious parts of how we define these derivatives. Just because we've got a lot of other things going on that we don't really need to cover that stuff. We'll just assume that it all still works the same way that it did back in Calc 1, because more or less it does. One quick thing that I should point out about these directional derivatives is that we are going to look specifically only in a direction and not a magnitude, which means that our vector, or the direction that we look at, needs to be in the form of a unit vector. So I need to divide its magnitude away. We did the same thing really when we did our x and y partials, because our directions there would be 1, 0 or 0, 1 respectively, and those are also unit vectors. You'll see if you plug in either of those vectors as your direction, you'll just get the x partial or the y partial of these things. But anyway, and enough about that example. Let's define the gradient, because it's going to be helpful to us. The gradient, it is a vector, which is important because we do look at both scalars and vectors in the course. So let's make sure that we know that the gradient is a vector valued function, or at least the result of the gradient is a vector. However, the gradient operator happens on a scalar function. So I take some original function, whatever f is, it's going to be a scalar value, something like f equals x squared plus y squared in the previous example, which is not a vector, right? That's just a scalar. X squared plus y squared is a scalar value, but its gradient will be a vector. And its vector is pretty easy to remember. It's just the x and y partials in their correct component places. So x partial in the x component, y partial in the y component. And when we upgrade this to 3 dimensions, we'll see that there's a z partial in the z component. Bet you never would have guessed that. So cool, that's our gradient. That's going to be its definition, and we're going to spend a lot of today just trying to figure out what the gradient is and tells us. But the first really nice thing about the gradient is that it lets us vastly simplify that directional derivative that we just looked at. Instead of needing to do some crazy limit as h goes to 0 of some unit vector being multiplied in, I can instead just take the dot product of my unit vector in the direction I want to be going in with the gradient of the function. So I'll still have my x and my y partials play a part in finding these directional derivatives. But ultimately, I'll just end up taking its dot product with whatever direction I want to be going in. So again, if my direction is just the x-axis or the y-axis being 1, 0 or 0, 1, this directional derivative will still return exactly the x partial or the y partial, again, if I'm looking specifically in those directions. So really, this directional derivative is just a way to find our derivative value for the bits that are in between strictly x and strictly y. The directional derivative, despite the fact that it relies on the gradient to come up with an answer, is a scalar result, right? Because it's going to be the dot product of a direction and a gradient, which means it comes back to being a scalar. It's the result of a dot product. I take two vectors and they create a scalar value. So my result is, again, should just be a number. I got 6 over square root 5. When I looked at this particular example, which was the same example we did a minute ago, but easier. Let's, yeah, bring up some more stuff about the gradient. If I wanted to look at the maximum rate of change of a function, we did this one a while back. We had that example about B's when we did the tangent planes. Right, we had some B density function, and we wanted to know which direction we should run in order to escape our B's. And we did that just with a tangent vector or a tangent plane, looked at the various directions we could run in to just minimize that tangent direction or that tangent value based on the plane. The gradient is going to do a better job of answering that question. The tangent plane just gives us an approximation for which way we'd want to go to maximize or minimize that rate of change. The gradient will tell us exactly which way to go. So in particular, if I wanted to know the direction that some function is changing the most, it's going to be in the direction of the gradient. Gradient returns our direction of maximum change. And the value of that directional derivative in the maximum change is just the magnitude of the gradient at that spot. So the magnitude of the gradient will give us our maximum rate of change, and the direction of the gradient tells us which direction that happens in. The real simple proof idea here is if I just look at trying to maximize this directional gradient, notice that the magnitude of u, which is the thing that I'm dot producting with, it should be a unit vector, so it has a magnitude of 1. That gets me from steps 2 to 3, right in between here and here. I'm saying that u has a magnitude of 1, so that's why it no longer shows up in the next line. And then if I'm attempting to maximize this value, I want cosine of theta to be equal to 1 because that's its maximum value, which means that the angle between my direction and my gradient would be 0 radians or 0 degrees. But it doesn't matter what unit system I'm in, I get 0 both times. So my directional derivative, again, will be maximized when my direction and my gradient are parallel, when they go in the same direction. So that's a bunch of the math for what the gradient will look like. I think in a minute, we'll start trying to explain some shapes and maybe get an even better understanding of what's going on there. Oh, cool. So if I wanted to find that maximum rate of change, I would just get my gradient and take its magnitude. And if I'm asking for the direction in which it occurs, I again want that thing to be a unit vector. So while the gradient itself is the very first thing I do, I'm going to split the question up into the gradient's 2 component parts, its magnitude and its direction. Because all vectors have both magnitude and direction. So oftentimes we'll answer a question like this with 2 parts, but they're really just both the gradient, just split up into its, again, 2 individual pieces. But cool, enough on all that. Let's go do some examples. So here's a function, f of xy. It's x over x squared plus y squared. And I want to do a few things. I want to find its directional derivative at the point 1, 2 in the direction 3, 5. So step number the first. I'm going to go look at that direction. Because right now it just gives me a vector, 3, 5. That thing's not a unit vector. So I'm going to start by figuring out what my unit vector would be in that direction, which means I need a magnitude of v, which looks like the square root of 9 plus 25, which is root 34. Oh yeah, starting off strong. Which means my unit vector, which I'll mark as u, is going to be 1 over root 34 times 3, 5. And for simplicity's sake, I'll just leave that 1 over root 34 on the outside for now. All right, now that I've got my big, try that again. Now that I've got my direction, let's go get my gradient. Let's go get our gradient. We're all in this together after all. So I should take a gradient of the function that I have. Recall that the gradient should happen to a scalar function and result in a vector. That vector, again, is just the x and y partials in order. So my first derivative looks like I need the quotient rule. So giraffes forego. That means g, which is x squared plus y squared, times f prime, which is 1, convenient, minus forego. That'll be f times g prime. F is x, g prime is 2x, so this will be 2x squared. Let's call it 2x times x. Just to really emphasize what I'm doing there. And then that whole thing is divided by g squared. So x squared plus y squared squared. And then I want my y partial. Looks considerably easier this time around. I think this is just negative 2xy over x squared plus y squared squared. Okay. Put my right angle bracket on there. There's my gradient. Just had to use a couple of my derivative rules from way back when, because this one was a slightly more complex function, slightly more complicated function. Complex implies imaginary values. We don't have that. I digress. I should now plug some numbers into the gradient. Those numbers in particular are going to be 1, 2. 1 for x, 2 for y. And I'm also going to pull out my denominator since it's common between both terms. It is 1 squared plus 2 squared, all of that squared. So let's call that 1 plus 4 squared. 1 plus 4. I don't know why, but I really didn't like my handwriting there. So let's try again. 1 plus 4 times. All that's left over is going to be the numerator. I've got an x squared minus 2x squared, which would just be negative x squared. So I'll call that a minus 1 plus 4. And for my y component, negative 2 times 1 times 2 is negative 4. And maybe I want to simplify that thing, call it 1 over 25 times negative 3, 4. And now I've got my constituent pieces. I have the gradient, which is right here. I have my unit direction vector, which is right there. So to get my directional derivative, I just want the dot product of those two things. So duf of 1, 2 is 1 over 25 times negative 3, 4, dotted with 1 over root 34 times 3, 5. And that ends up being a fraction. My denominator will be 25 times root 34. Let's just get those pieces out of the way. And then just solve the dot product. I've got a negative 3 times 3. I must have done something wrong. Hi.
Be negative. You flip the negatives.
I very much did flip the negatives. Yep. I didn't even hear the whispering that time. Just looked up and there are hands everywhere. And I'm like, yeah, something's wrong. Yeah, 3, negative 4, for sure. which means this should be 3, -4 right there. Now I think it looks a little better. Yeah, first example, and it's already gone awry. Well, maybe we got it out of the way early. The rest of it'll go great. But now I need a dot product of those two pieces. I've got a +3 times 3, which is 9, and a -4 times 5, which would be -20. 9 minus 20, -11. Cool. So if that is our directional derivative in our first example, the next example is going to ask us to maximize some rate of change, which means that I only need the gradient this time, because the gradient will also give me my direction. So starting with the gradient, just as is. I just need my partials all in order. So this is going to look like y cosine xy. And then that's x cosine xy. Uh-oh. +1. Oh, never mind. That whispering died down quickly. Maybe that wasn't a me thing. So yeah, took my derivative of sine and got cosine. Chain rule says I multiply the other piece on the outside. I think that's our gradient. We also just sort of shadow implemented the z component, but I think that went all right. So let's move on to plugging our point in. 1, 0, 1 goes to some other vector. If y is 0, then that first component is 0. Can ignore that. Next up, this time I've got x and y are 1 and 0. So I've got 1 times cosine of 0. Cosine of 0 is 1, and 1 times 1 is 1 is 1. Cool. So 1 for that first one, and 1 for the last part. I don't really know why I put a +1 in the gradient when I could have just put 1. Guess I really wanted to emphasize that that number was positive after the last time. Let's go with that, and not some other strange explanation. So I've got my gradient now, which is the only part I need to answer the question, but I do again need to split up its pieces to get gradient f the magnitude, which is going to be the square root of 2. Square root of 0 plus 1 plus 1 would be just square root 2. So I'll keep it right there. And I think it also wants the direction, right? So that direction, over here I've got a little bit of, come on, there you go. Just slide you out of the way for a second. To go get that direction, which we'll call u, it should be the gradient divided by the magnitude of the gradient, which is going to be 1 over root 2 times 0, 1, 1. And I could probably leave it there, or I could call this thing 0, root 2 over 2, root 2 over 2, if I wanted to rationalize it. Either method's totally fine. Oftentimes I recommend staying with the top value, just because the less arithmetic you do, the fewer chances you have to make silly mistakes, like I make all the time. But if you prefer to use it with everything multiplied in, maybe that second one would be slightly easier to work with in some cases. Doesn't particularly matter though. Either form is fine. So either of those work, and then also that was our magnitude. Okay, so if that's maximizing our directional derivative, what about minimizing the directional derivative? That's the other thing we might want to do. Well, one of the other things we might want to do. So if we think back to, again, that B question, we had our B density and we're trying to run away from our B's. We weren't trying to maximize our rate of change because we did not want to run into even more B's. We wanted to run away from the B's. Which means we are looking for the direction in which our number of B's is most negative. Or ideally most negative. That's our dream here. So if we're looking to minimize, we want to minimize our rate of change, then we should run in the opposite direction of whatever our gradient is. If our gradient tells us the maximum rate of change, the opposite direction of the gradient, negative gradient, will tell us the least or the minimum rate of change, the way that the thing will get the smallest the fastest. And the value of that minimum rate of change is just the negative of the magnitude of the gradient. So same operations we've been doing, we're just going to flip the sign on everything that we've got. For some other bits, so suppose f is a differentiable function, it sees no change. So in the we're going to think the directional derivative is 0. Or if we want to find a spot where the function isn't changing at all, so where our directional derivative ends up being 0, which must happen somewhere, if our regular maximum direct change is positive, because it's a magnitude of a gradient, and our minimum rate of change is negative, because it's the negative of a gradient, it's got to hit 0 somewhere in there. And if both of our maximum and minimum are going to be parallel to the gradient, then we'll hit 0 when we're exactly perpendicular to the gradient, which is going to be a particularly helpful idea, especially when we get to the next section. Because, of course, the very first thing we want to do with our derivatives, once we learn what they are, is start setting them equal to 0 and seeing what that tells us. So that's where we're headed with this, just as like a bit of foreshadowing. We'll be setting these gradients equal to 0 a fair amount. But I digress. Let's come back to the thing that we're after here. We want to take another example, find its gradient, and look at some stuff. So gradient f. Oop, I forgot to change my pen back to the black pen. Gradient of my function, which is y squared over x, looks like negative y squared, y squared over x squared, and then 2y over x. I think that's my gradient. If I just look at my two partial derivatives, I get that. Then I want the gradient in P's direction, which will just be the gradient at 1, 2. So I plug those numbers in. This looks like negative 2 squared over 1, which is negative 4. Don't forget the negative, geez. And then 2 times 2 over 1 is positive 4. Plug that stuff in. So to find the rate of change of f at p in the direction of u, I need a unit vector. So let me go get that real quick. Magnitude u is going to be 1, nope, try again. The square root of 2 squared, which is 4, plus root 5 squared, which is just 5. 4 plus 5 is 9, and the square root of 9 is 3. So magnitude of u is 3, which means when I go to get my directional derivative of f at 1, 2, it's going to be negative 4, 4, dotted with 2 root 5, times 1/3 to divide away that magnitude. So in the end, this is 1/3 times -8 plus 4 square root 5. And again, back to being a scalar quantity. Right? Because my directional derivative should be a scalar, even though my gradient and my direction are both vectors. In the end, I'm always taking a dot product of those two things. So the directional derivative itself is a scalar value. So think of it like the speed, where it's just a number and not a direction, since we usually like to think of rates of change in terms of how fast something is going. So speed and velocity are things we go to like all the time. But if I want to find a direction, I'm going to call it v, in which this function is neither increasing nor decreasing. Well, how do I want to do that? I suppose I should first define my vector v. I'm just going to call it v1, v2, so that I have just some arbitrary values I can work with. I know that this should be a unit vector, so blah, 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 blah. Stop it. v1 squared plus v2 squared should be equal to 1. I've got that equation I can set up. Again, my direction should be a unit vector, so the two components squared ought to be equal to 1. And I set all of that up so that I could get -4, 4 dotted with v1, v2. And I know that that should be 0 because I want my directional derivative to be 0. Which gives me the equation -4v1 plus 4v2 is 0, which means that v2 and v1 have to be equal. So maybe the simplest vector you could come up with, instead of needing to go over and solve that other equation, you might be thinking, just 1, 1 works really well for our direction, since v1 and v2 are equal. And that's like not a bad idea at all. That is going to be parallel to our direction. The only problem with 1, 1 is that it's not a unit vector. So we should go, solve to get that unit vector. Or alternatively, make 1, 1 a unit vector. Just multiply 1 over square root 2 here, and you'd be done. But let's go over a more formulaic way of getting there. If v1 and v2 are equal, that really means I have, I don't know, how about 2v2 squared is equal to 1. If I come back to my magnitude equation, you'll just pop that right there, draw an arrow saying, hey, look, I'm going to go plug in right there, right into that equation. v2 and v1 are equal. That means 2 times v squared is 1. So v2 squared is a half, meaning that v2 is plus or minus 1 over square root 2. So I actually end up with 2 directions. V is going to be plus or minus 1 over square root 2, 1 over square root 2, or more commonly, that's root 2 over 2, root 2 over 2. So a 45-degree angle, or pi over 4 radians, if we were going to go measure our direction that way. So I found 2 directions where this thing was something. 2 directions where our gradient was equal to 0. Or our directional derivative was equal to 0. The magnitude of the gradient is not relevant there. Yeah. Because again, the thing that we talked about earlier is that these vectors right here should be perpendicular to our gradient. There we are. Those are the words I was looking for. So to simplify this, the vector 1, 1 is going to be perpendicular to the vector -1, 1. Or -4, 4. To use the exact numbers we had there. Simplifying a little bit, pulling a number out. But yeah, enough fun on that. So we've talked a bunch, sort of broadly, about how this gradient, which is a vector, should point in the direction of maximum change. We're trying to maximize our rate of change. But what does that actually look like on some graph, or more accurately, on some contour plot, right? If I gave you this shape and said, draw the gradient at P, how would you do that? And what would it mean? Well, let's try and gather some of that understanding. Before I look specifically at point P, I want to maybe give some sort of a context for this shape that we're looking at, right? We're just told it's a contour plot. So we can kind of just make up whatever story works to sort of explain the shape that we're seeing. And so rather than having you make one up, I'll try and give us something that at least will guide our thinking. Think of this contour plot maybe as some ripple that is expanding in water. Never mind the fact that it's like a weird looking ripple because it's all generating out of one point instead of out of its center, but look past that part for a minute. Imagine again that there's some sort of device right at the origin that's creating ripples that are moving outward from it. And those contour plots that we're looking at are ripples at different points in time. Right? So this thing is expanding outward. So if I just come and look at the top part here, these ripples are expanding outward. Blue for being in water. Same thing if I look at the next one down. And even like the little guy in here. All right, so again, I want to think about this as like a ripple out in water. If I'm looking at the rate or the spot, the direction in which any of these places are expanding the fastest, they're going to be directly out from its shape. Or in other words, they're going to be directly normal to this shape. If I were to look at just the part that's on the y-axis, that point of the ripple is moving only outward in the positive y direction. It's moving just straight up. Right, that's the direction that point is going. It doesn't have any x or y movement at all. So its maximum rate of change is in a direction that's directly up, straight in the y direction. If I were to look in a direction to see the way in which its rate of change is maximized, it's straight in the y direction. Any deviation from straight up will give me a smaller change because I'm not looking at the most change I could have. And conversely, if I look in the strict x direction, so either positive x or negative x, look left and look right, that point in the ripple, that point in this wave that's expanding out in the water, isn't moving at all, left or right. So its directional derivative in a left or right direction should both be 0. Because again, that point isn't expanding out at all there. Unless, its minimum direction would be just look backwards. So its minimum rate of change would be going back straight down the y-axis. But the point I want to be trying to drive at here is that the gradient, which is the maximum rate of change, or at least the direction of the maximum rate of change, should point normal to the surface or perpendicular to the surface. So if I bring that back to the point I'm actually looking at, P right here, I want just a normal vector. Something about like that. That's going to be its direction, its direction of maximum change. To maybe try that example another way. Contour plots. Because, maybe if you look at that last shape, this looking back at point P, it might seem sort of natural to think that the maximum rate of change should occur in a tangent direction. Since you're just looking at the circle as a path that you're traversing, maybe it kind of makes sense that a tangent vector should give you that maximum rate of change, because that's just the way that the graph is going. Which is a bit of a weird idea. So I want to try to give an argument against why the tangent direction should be maximum rate of change. And I want to do that by looking at a contour plot of a mountain. Right, so Lonesome Mountain right here, the peak is right where the word Lonesome Mountain is. You've seen one of these graphs before. All of the pink lines are showing locations of equal altitude. Right, so if I'm looking along maybe one of those points that's labeled 4,500, or that one's maybe a little harder to see. How about we do 5,500? It's that point right there. I don't know why I keep pointing at the board when I get the circle stuff. Every point along that pink line labeled 5,500 has an elevation of 5,500 feet. So that means as I go more toward the peak, just again, right there in the center at Lonesome Mountain, I'm going to be gaining in elevation. And so my function here, if I'm looking at this contour plot, my function should be describing the elevation of every point that's on this mountain. So if I want to talk about the direction of maximum change, I'm talking about how my elevation is changing of this mountain. That's the thing that ought to change. So I'm looking for my direction of maximum change. That's going to be just up the steepest part of the mountain. I could see maybe over here in this section, it's really, really steep because all those contour plot lines are bunched together. That's a pretty sheer cliff right there because my elevation is changing very rapidly. So my direction of rate of change goes straight up all of those increasing contour lines. And then my minimum rate of change would just be going straight down the mountain. But if I were to stay along one of these contour lines, right? If I just traversed directly along the line that was drawn on there, that means I'm staying at, in this case, an elevation of exactly 5,500 feet. So walking along the contour line means my elevation doesn't change at all. Or in other words, my directional derivative along that path is 0 because my elevation's not changing. The thing that I'm measuring is my elevation. If I stay along a contour line, my elevation does not change. So tangent to these curves is going to be a directional derivative of 0. So then its maximum rate of change will be perpendicular to those contour lines, or again, normal to those contour lines. To pull everything together into a way that hopefully we'll get to, and hopefully is a thing that I've written down right here. Yeah. This gradient function should be perpendicular to my surface. So perpendicular to the level curves of my function. Again, those level curves being the contour lines that we were just looking at, with either the elevation example or the ripple moving through water example. My gradient gives me something that's perpendicular to all my level curves, which means if I'm thinking of that whole thing as a surface, my gradient should be normal to the surface. And once again, I've got a scalar function, but the gradient of that scalar function is a vector. I can step it up to 3 dimensions by just adding a z partial in. My directional derivative was here. And I want to just comment on one other element that I think shows up first in this section, where we start to see it in other places, where we start using the x vector to represent our variables. instead of having to write a function of f of x and y and z, oftentimes we prefer to be lazy and just write it as a function of x vector hat. So if I put a vector hat on my x, that just means it's supposed to represent all of the variables I'm working with, or all of my parameters. So in 3D, the x vector is xyz, because it contains all three vectors. And in 2D, the x vector is just x and y, because it's only got the two variables, the two parameters. And I can see with that long-winded explanation, I maybe won't have time to finish everything today, but well, maybe that's fine. We'll see how much more of this we can get through. So again, directional derivative, got all that kind of fun stuff. Based on the last explanation we went over, and if I could emphasize just one thing, it's that this gradient should be perpendicular to the level curves, or it should be normal to the surface. And if it's normal to a surface, meaning maybe I have some sort of normal vector that my gradient creates, it should be pretty easy to turn a normal vector, i.e. a gradient vector, into a tangent plane. Since in order to get a tangent plane, I just need a normal vector and some point to be normal to on my surface. So again, derivatives, we always want to be thinking that derivatives and tangents are very closely tied together. So that's really what they do. Since this gradient just is a collection of derivatives, there ought to, again, be some connection to a tangent idea. In particular, it gives us the normal vector for the tangent plane. So if I want to go do some of that stuff, maybe find gradient f of this function. Also notice that my function's equal to a constant value. That's pretty important when we're setting this stuff up. Make sure that our function should have all of its variables gathered on one side, and then its constant term on the other. Oftentimes that constant will be 0, but in this case it's 3. It doesn't super matter to us. But I should make sure that my function is equal to a constant before I start doing extra math. So I want a gradient of this thing, and it should be some stuff. This looks like y plus z, and then x plus z, and then x plus y. No, x plus y, not x comma y. Adult. And then I want to plug in my point 1, 1, 1. So gradient f or grad f looks like 2, 2, 2. Right, whoop, I forgot a part. Slide that out of the way. This was supposed to be at 1, 1, 1, 1, 1, 1. There we go. And again, once I have my gradient, that thing is my normal vector. So with a normal vector, I can then put that into the equation of a plane. Oh, we didn't even need to do that. Never mind. Here we were just looking for the normal vector. Right, vector perpendicular to that thing at 1, 1, 1. It's just that. But if I wanted to find the tangent plane, I could just plug that into the equation of a plane and go from there. But I think we have another example to look at that'll do that. Because yeah, here we go. So an even stronger definition and written out more clearly. If I want to find a tangent plane to some surface, I should just find the point I want to be tangent to and collect the gradient at that point. And that just turns into the equation of a plane. So recall the equation of a plane should be a times x minus x naught plus b times y minus y naught plus c times z minus z naught. And those a, b, c values are just going to be our function's partial derivatives at x, y, and z. Again, coming directly from the gradient. since I know my normal vector should be equal or at least parallel to my gradient vector. So let's find a tangent plane. And I'll leave that part on screen. So first step, I should be looking for the gradient of my function, which is 2x, 2/9 y, and 2/9 z. And then I want to plug my point into that gradient vector. So 1/3, 2, 2 gives me 2/3, 2/3, try again, 4/9 and 4/9. And again, I'm going to claim that that's my normal vector. So to find my tangent plane, I just need to start plugging a bunch of stuff in. 2/3 times x minus 1/3 plus 4/9 times y minus 2 plus 4/9 times z minus 2, all equal to 0. Or to just highlight some bits, that 2/3, that 4/9, and that other 4/9 all come from my gradient, because that's my normal vector. And I'm just plugging those gradient values into the equation of a plane for A, B, and C. And then maybe I could simplify this thing a little bit. Call it 3 times x minus 1/3 plus 2. Yep, 2 times y minus 2 plus 2 times z minus 2. If you were particularly allergic to fractions, I just multiply the whole thing by 9, divide the whole thing by 2, just to simplify those values out in front. I get the same stuff. I'll leave that alone for now because I think I've got 2 minutes left, and that might be just enough time to look at the final example. So if I've got a tangent plane, I could also look at a normal line because my gradient gives me both. Right? If I have a normal line, we call it lines parametrically or just some direction vector times t plus some point that initializes my line. So my direction vector or the normal line will be the normal vector. Again, that's the gradient. So just gradient times t plus whatever point I want to be passing through. So the same point I would use to find a tangent plane, same point I want to be tangent to, I'll use that in the normal line. So if I want to find this here tangent plane, I should define myself a function, which is going to be function is z minus x squared plus y squared equals 0. Again, make sure when you're starting to do all this math stuff, our function, if it's going to have all 3 variables in it, needs to be a thing that is equal to a constant. So in the case where I've got z equals x squared minus y squared, I want to move all of my points over, all of my variables over to one side first. So get them over there. And then I'll take a gradient of that thing. So grad f is the vector negative 2x, 2y, 1. And then I can plug in my point, 4, 3, 7, to get negative 8, 6, 1. And again, this is my normal vector. And I'll use that to come up with the equation of both my tangent plane and my normal line. So for the tangent plane, this is negative 8 times x plus not 8 times x minus 4. There we go. Plus 6 times y minus 3 plus 1 times z minus 7. Pop those two guys in red. And keep in mind that I'm taking that point and plugging it into the plane equation. Of course, I'm forgetting a rather critical step for the equation of a plane, and that's setting it equal to something. So let's set it equal to 0. And for my final trick, which I'm sure I'm out of time for, but I'm gonna do anyway, my normal line, -8, 6, 1, that vector, times t plus my position vector, the position vector for my point, which was 4, 3, 7. Again, normal line and tangent plane are just built of the same components, but organized differently. One's a plane, the other's a line. One's a scalar equation, the other's a vector valued equation. Yep, definitely over on time. So I'll end it here, and I will see you guys again on Friday, where we're going to do optimization. Okay, bye, 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 bye.